Hello, Tensor friends. This is the problem of the day for 624. Very exciting. Okay, a little bit of background. In 1869, Elwin Bruno Christoffel published this. Let's listen to it.
Über die Transformation der homogenen Differentialausdrücke zweiten Grades.
Okay, I really am going to try to attempt that. Here's what it means on the transformation of homogeneous differential expressions of the second degree. Now, I'm going to translate this into modern syntax. He simply asks this question: how does a vector change with respect to a coordinate? So let's go look at that. Okay, what we have here is kind of obvious. We have a circle, has a radius. The radius is away from this coordinate line, defined by this angle, the theta, which goes in a counterclockwise direction by convention. And at a point on that circle, we can define our regular Cartesian basis vectors. We can also define these polar basis vectors, which you derived in the problem of the day, ER and E theta. Now, what he was asking, it's not exactly what he was asking, but this is what he meant. I'm reading into his German, okay? Is when you change this point around this circle, look at what happens to the red basis vectors, the Cartesian basis vectors. Nothing. They remain the same. That's why they're so beautiful and easy to use. But look what's happening to the polar basis vectors. They change direction every point I move. And the E theta basis vector even changes magnitude when I increase R, and it reduces when I decrease R, right? So they're not only changing direction, but one of them is changing magnitude. So he said, what's up with that? That's what he did. Okay, so we have a vector which we write in summation notation. So what is the change in that vector with respect to an arbitrary the coordinate? Well, we use the product rule here, right? First times derivative of the second plus the second times derivative of the first. And then you say, well, what is this? What is the derivative of a basis vector with respect to a coordinate? Okay, well, you can see we have two free indexes here, and the derivative of a vector is a vector, which can be expressed as a linear combination of its components and basis of vectors. So since we have these two covariant indexes, they have to go there. Basically, that makes that a summation index, okay? Now, I downloaded his the paper. I could not find an English translation of it, so I spent an enormous amount of time translating individual sections and trying to follow his math. It was very difficult. And I made 3 videos on that. And the first one was how he came up with this. And there's a link to that in the description of my video, doing my best to explain how he come up with that. Okay. And in that same paper, I made 2 more of the videos. He derived what would become the covariant derivative, and I made a video of that, and what would become the Riemann crystal curvature tensor. So there was a lot going on in that first paper that he published in this, and it was truly the beginning of differential geometry. A differential geometry had been started by Gauss and later described by Riemann, but unfortunately he died very young and he never got to finish it. But this is where it really got off the ground, is you could have hard equations to work with in differential geometry. Okay, so that's a long-winded background of what we're doing here. Okay, given the format of Christoffel the symbols found using the metric tensor, okay, this is the format that everyone uses to find the metric tensor, okay? And you can see here you have 3 free indexes, I, J, K. And so you know you have to put them in the same place. So K has to be in a contravariant position. The I's and J's have to be in the covariant positions, right? And the easy way to remember how to write this thing out without looking, because you can go writing this around, it really impresses girls. I'm kidding. It does not. Okay. Is that The first one you write down is the inverse metric, the tensor, and you only got, like I said, one contravariant component. So the next one has, because you have two input holes here, right? You have to put something there, so you know it's going to be a summation index. Okay, and the ij in the covariant position always goes with the negative part of this equation. So you always put ij here. Now you have nothing left to put here, so that has to be a summation index. Then in the first two positive terms, you can put an I here or a J here. It doesn't matter. You just start with an I and then put the opposite free index down here, J. See? Here is a J, opposite index is I. And then that leaves only one hole left each, so there has to be a summation index. That's how I remember this. Now I can write it down without looking at it. Okay. And we were given, or you derive this in the very last the problem of the day, Gij in polar coordinates, which was this. The inverse of that is obviously easy because you just put these two under one, and you got that. Find these three non-zero Christoffel symbols. There's only three non-zero ones, okay? So you're going to use this and this in here and find those three components. All right, part B. Did I call that part out yet? My brain. Part B. Using the definition of the Christoffel symbol, boom, and the basis vectors, prove that these two Christoffel symbols are equal when you exchange their lower indexes. Okay, I'll have the solutions a couple days. I'll see you then.